In this last section of Chapter 5, we're going to look at normal approximations to a binomial distribution. Normally, with normal distributions, it's a continuous distribution, but binomials are discrete, and they can be impractical for some uses. For example, suppose you wanted to find the probability that less than 100 out of 150 surgical procedures had been successful. Well, if you're doing binomial, then you would have to do the binomial formula 100 times and add all those resulting probabilities. That would take a while and not very practical. A better way to do it would be to use a normal distribution approximation for the binomial distribution. And as long as NP and NQ are greater than 5, then the binomial random variable x is approximately a normal distribution with a mean, mu equals np, and a standard deviation, sigma equals the square root of np cubed. So, we do need that np and nq being greater than 5, but other than that, it allows us to do an approximation, use the table 4, z-scores, and so forth to do our probabilities. Now, it is important to do what's called a continuity correction. You use when you use a continuous normal distribution to approximate a binomial distribution, basically you move 0.5 units to the left or right of the midpoint value, so that the interval will include all possible x values that you want to. So here we have a little table to help, but again, when you've got a binomial, you're basically finding exact values at the center of each of these intervals. However, when you are doing a normal distribution, to make sure that you are including the points that you want to include, we have a little correction factor, 0.5 to either side, depending on the situation, and our table summarizes it. So if we wanted to get exactly on a certain value, then basically we would do two different z-scores. We would do one for 0.5 less than x, and then one for 0.5 greater than x. If we wanted at most c, then note how this x is less than c plus the 0.5. That 0.5 just makes sure that we are including x as part of the solution. Fewer than c, then we go in this direction, and then at least c or more than c. And again, you can see some of these will include c, in other words, the actual value you're trying to find, whereas other ones do not. And so we have to make sure and use the appropriate one. So that's pretty much it for Section 5. Let's look at some examples to make this a little bit clearer. So let's suppose we have a survey, and in that survey, 47% of 8 to 18-year-olds who are heavy media users say they don't get very good grades, fair to poor. Now you randomly select 45 of these users, and the question is, what is the probability less than 20 of them will say they get fair to poor grades? Now again, if we were just strictly doing binomial distribution calculations, we would have to do 20 calculations, add them all together to get this probability. Instead, we want to see. All right, first off, how about NP and NQ? Well, NP, 45 times the 0.47, that gives us 21.15. NQ, the 45 times the 0.53, and just as a reminder, 0.47, 0.53, have to add up to 1. P plus Q equals 1. So they're both greater than 5. We can use the normal distribution approximation. So the mean, NP, same one we had here, 21.15. The standard deviation, NPQ, 45 times 0.47 times 0.53. Square root, we get 3.35. Now, we're not going to do 20. We're going to move it over a little bit because we want less than 20. So we don't want to actually include the 20 in our probability, so we go a little bit less than that. Now we find our z-score. So 19.5 minus the mean of 21.15 divided by the standard deviation gives us negative 0.49, which then using the table would give us 0.3121 to the left. In other words, the probability that fewer than 20 would say, yeah, they got poor grades or fair to poor grades would be approximately 31.2%. All right, second example. We have a study of NFL retirees, 50 years and older. We found that 62.4% have arthritis. You randomly select 75 NFL retirees who are at least 50 years old. What is the probability? Exactly 48 will say they have arthritis. So again, we check our NP and NQ. They are both greater than 5. Let's go ahead and find our mean and standard deviation. The mean comes out 46.8. The standard deviation comes out 4.19. Now in this case, since we want to find an exact value, exactly 48, we had to do our correction on both sides. 0.5 less than the 48, 0.5 greater than the 48. We will then do two different z-scores, one for the 47.5 and one for the 48.5. And then we subtract between the two. And in our subtraction, basically what we're doing is we're finding, if we go back to our picture up here, we're finding this band between the two values. And so exactly 48, sorry, typo there, subtract the 2, and we end up with about a 9.2% chance of having randomly select 75 retirees. 48 out of that 75 would have arthritis. And so that is section 5-5.